So now that we know what eigenvectors and eigenvalues are, we're going to end the section 3.4 with a few extra facts and important definitions that you should know. And here's our definition. If lambda is an eigenvalue of a square matrix A, then the eigenspace for lambda is the set of solutions to the equation a minus lambda in times x equals 0. So remember, this is the equation that we were solving to find the eigenvectors corresponding to lambda. And this solution set is called an eigenspace. One detail that I want to point out is that one of the solutions to this equation is, of course, x equals 0, but the 0 vector is not actually an eigenvector, even though it is included in the eigenspace. So the name eigenspace was chosen for the reason given in this theorem. If you have some n by n matrix with the eigenvalue lambda, then the eigenspace of lambda is actually a subspace of Rn. And we're going to check half of this theorem. We're going to check closure under addition. So what that means is if we start with two members of the eigenspace, two eigenvectors corresponding to lambda, then we have to show that the sum of the two vectors is also an eigenvector corresponding to lambda. So just work through. When you multiply by a matrix over a sum, we can distribute. So this is really ax1 plus ax2, and that's going to be equal to lambda x1 plus lambda x2. That's because we know we started with eigenvectors corresponding to lambda. And then we can factor out that eigenvalue, factor out the lambda. So we actually do end up with lambda times x1 plus x2. So you might have noticed that finding eigenvectors and eigenvalues can be a pretty long process. But if you're lucky enough to start with a triangular matrix, then it's actually quite easy to find the eigenvalues. And here's what they are. The eigenvalues of a triangular matrix are just its diagonal elements, so just the numbers on the diagonal. And the reason is down here. We won't go through a formal proof, just an example. If I was wanting to find the eigenvalues for this matrix, I would need to set up this determinant of a minus lambda I4. And what this is going to do when you carry out this subtraction is subtract lambda from each of the diagonal elements. And we're still looking at an upper triangular matrix, and when we're computing the determinant of an upper triangular matrix, we just look at the product of the diagonal elements. And I've written that out here. So that's just 1 minus lambda times 5 minus lambda times 8 minus lambda times 10 minus lambda. So when you've computed the determinant, it's already factored out, and the solutions are already given to you.